So here is the first question. We're going to start off with some exponential functions today. Let's say I want to solve an exponential function. Let's say I have 3 to the power of 2x equals 5. So notice for this example, the bases are different. I also have an x in my exponent. How do I get x by myself? Hopefully you know this already. I am going to take the log of both sides, specifically the log base 3 of both sides. Log base 3 of 3, log base 3 of 5. The reason I do that, notice the log base 3 and the 3 will essentially cancel out, leaving us with 2x on the left side, and on the right side I can't simplify that. It's log base 3 of 5. I'm going to divide both sides by 2, and I'll get a final answer. I don't think you're allowed a calculator on this exam, are you? Or maybe a scientific one?
We're allowed a scientific calculator, but not a graphing calculator.
Gotcha. So I'm assuming this answer is fine in the final form. You could also probably plug this in a calculator, but honestly, I'm fine with this, and I'm sure your professor would be as well. So the moral of the story, whenever you have an x in your exponent, the only way to solve for it, to get it out of that exponent, is to take the log base whatever of both sides. Now, in this case, we had log base 3. Log base 3 is kind of rare. Typically, we deal with the natural log. In other words, we're looking at functions like this, e to the x squared, something like e to the x squared plus x, let's say minus 4, something along these lines, is equal to, on the right, I'm going to put e to the, let's say, negative 2 power like this. So this is a slightly different example. One thing you can do is you can take the natural log of both sides, which if you remember, natural log is the same thing as log base e. It's called the natural log for a very specific reason, which I'll probably talk about today. But you don't actually have to do that for this problem because we notice the bases are the same. And whenever the bases are the same, you can set the two functions equal to each other, the two exponents, that is. So in other words, I have x squared plus x minus 4 is equal to negative 2. To solve this one for x, notice it's a quadratic. It means I'm going to add 2 to both sides. So x squared plus x minus 2 on the left. On the right, I now just have 0. Now I can factor this. Hopefully you guys are good at factoring. It would be x plus 2 times the quantity x minus 1 equals 0. We get two solutions for this one. X equals negative 2 and x equals positive 1. I'll give you a few seconds to write that down. But again, the strategy for this one, whenever you have an x in your exponent, in this case the bases were the same. Right? We can literally set the exponents equal to each other. But just, you don't have to write this down. I'm just talking out loud. If you have, let's say, e to the 2x equals 5, then you would take log base e of both sides, which is the natural log. Natural log is log base e. So that's what you would do if the bases are different. When they're the same base, you set the exponents equal to each other. Hopefully, that's all review. Now, next thing I want to talk about, this is kind of the hardest case you have with logarithmic functions, and that is, what do we do if we have something like this? Let's say I have 5 to the power of 3x is equal to 25 to the power of, let's say, x squared. This is the worst case scenario. Why? Because the bases are different, and I have x in both exponents. I have 5 to the 3x power and 25 to the x squared power. Here's what I recommend you do for this one. We see that 5 and 25 are like a square and a square root of each other. We are going to use that fact to help us solve this problem. The first thing we need to do is we need to choose a common base. It's either going to be base 5 or base 25. My recommendation to you, always choose the lower base. Choose lower base. That's going to be our common base. In this case, it's 5. So the left side I'm going to keep the same, 5 to the 3x power. On the right, I have 25x squared. So I'm going to rewrite that as 5 squared now raised to the x squared power. So now I have the same base. It's 5. But before I set the exponents equal to each other, remember I have a power raised to another power here. I have 5 squared raised to the x squared power. Don't actually shout this out loud. This is a rhetorical question. But what do you do if you have a power raised to another power? Hopefully we're all thinking it. You're going to multiply it. So it's going to be 5 raised to the 2 times x squared. And that's because a power raised to another power becomes multiplication. So I'm saying 5 to the 3x power equals 5 to the 2x squared power. Now the bases are the same. I can set them equal to each other. I get 3x equals 2x squared. Very nice. Now if I want to solve for x, a lot of people have trouble with this part. A lot of people like to cancel out one of the x's here. If you do that, you're losing one of your solutions. So don't do that. Instead, what we have to do is, since it's a quadratic, again, x squared, we need to get all the x's on one side, literally everything on one side, and 0 on the other. So I subtract 3x from both sides. I get 0 equals 2x squared minus 3x. Now it's still not obvious what we do. We don't need to do quadratic formula. What we're going to do is I'm going to factor out the common term, which is x. So 0 equals x times the quantity, 2x minus 3. That's what's left when I pull out x from both terms. And now I'm going to set both of these terms equal to 0. X equals 0 and 2x minus 3 equal to 0. The first solution's obvious. It's right there. X equals 0. The second one, it's pretty easy to find. I add 3 to both sides. 2x equals 3. And then x is going to equal 3 halves. So this one had two solutions. X equals 3 halves and x equals 0. And again, the strategy, I had different bases and an x showing up in both exponent. I had to take a common base and always choose the lower base. Any questions on what we've seen so far? Anyone still writing? Okay, great. So that's pretty much all I wanted to say on exponential functions. Actually, if I were to say one more thing, this is actually kind of helpful to know. Let's say I have e to the 5x times e to the 3x plus 1. How do I simplify this? Well, if you remember, whenever I multiply things with the same base, it means I'm going to add the exponents. And when I add the exponents, it's e to the 5x plus 3x plus 1. That's just going to simplify to e to the 8x plus 1. This is going to help us a lot when we're taking derivatives of some of these functions. Like imagine if I asked you to take the derivative of these two. Well, I mean, the one function, multiply the two things together. This would be a product rule, right? Because we're multiplying two things together. However, we can avoid the product rule if we know our properties of exponents and we just rewrite it like this. I'll talk about derivatives of exponential functions next, but one more thing first. I want to talk about division now because division's annoying. Let's say I have, one last example, e to the 2x plus 1 divided by e to the 7x minus 4, something like this. How would I simplify this? Well, if multiplication was addition, division's going to be subtraction, and you have to be careful because we need to subtract the whole quantity, 7x minus 4. In other words, what we have here is e to the power of 2x plus 1 minus the quantity 7x minus 4. A lot of you try and be heroes and solve this in one step. I wouldn't because, well, I like getting the right answer, so I would do this in 2 steps. I write it as e to the 2x plus 1, distribute the negative sign to both terms, so minus 7x, and then minus a negative becomes plus 4 now. And now I can combine like terms. E to the 2x minus 7x is negative 5x, plus 1 plus 4 gives us plus 5. There is the final answer to my question for this problem. Any questions on that one?
Since you had a negative exponent, would you have to bring it down to the denominator?
That's a good question. So sometimes you'll see that in the answer choices. Sometimes you won't. My advice to you is, notice how for this one, it's e to the negative 5x plus 5. Since one of the terms is plus, I would say this is fine. What you really run into trouble is sometimes, depending on who it is, like I would keep this as this answer. Like let's say I had e to the negative 5x minus 5. Then technically what you could do here, since they're both minus, you can factor out a negative sign. You have e to the negative now 5x plus 5 power. And remember what a negative exponent means. It means shove that sucker in the denominator. E to the 5x plus 5 in the denominator now. Again, both of these are correct. Do I know what? I think your professor would accept all of these, unless it's a multiple choice question and you only see this one in your answer choices. So again, why did I put this one in the denominator and not the one above? Well, because it was minus 5x minus 5. Everything was negative. If I so much as have one positive, I'm going to keep it in the numerator. all day, every day, because it really doesn't look that much nicer. Like if I were to rewrite this, what would this look like? Think about this for a second. It would be 1 divided by e to the positive 5x minus 5. Does that look nicer than what we have right here? I don't think so. I think this is just as horrible. So I like both of these. Does that answer your question?
Yes, thank you so much.
Yep, no problem. I'm assuming your professor did not explain this. Why would he or her? They are not paid to teach. They are paid to do research for the university, and that is my on-the-books opinion on that. Don't tell your professor I said that. They're great. Okay, now for the next one, we have... Oh yeah, that's it for exponential functions. Now I'm going to move on to exponential derivatives. Exponential derivatives. So when it comes to exponential derivatives, the derivative of exponential functions, the one cool thing, and there is exactly one and only one cool thing about exponential function derivatives, and that is the fact that if I have the function y equals e to the x, it is the only function in calculus whose derivative is itself. That's pretty cool. At least I think so. Now if I had y equals e to the 2x, now all of a sudden the problem is impossible. I have e to the 2x in my exponent. Don't worry, it's actually possible. Didn't mean to scare you. But all you need to do is say to yourself, what's the derivative of my exponent? 2x? Okay, well the derivative of that is 2. So my overall derivative is going to be 2e to the 2x power. This is not a power rule. I repeat, this is not a power rule. We did not subtract 1 from the exponent. We took the derivative of the exponent, put that in front, and then multiplied it by the original function. That's how you take the derivative of exponential functions. Let's look at a couple more, and then we'll look at those complicated ones that some of you were asking about at the beginning. So let's say I have y equals 3e to the square root of x power. This is especially dubious, whatever. Well, if my exponent is the square root of x, I can rewrite that as x to the 1/2. I need to ask myself, what is the derivative of x to the 1/2 power? That would be a power rule. 1/2 times x to the, what's 1/2 minus 1? Negative 1/2. So it's 1/2 x to the negative 1/2 power. That goes in front of everything, along with that 3 there, since the 3 right here is just a coefficient. So it's going to be 3 times 1/2 x to the negative 1/2 power. I can rewrite that in the next step. And then times my original function, e to the square root of x, or you can write x to the 1/2. It doesn't matter. And this would be our answer. Can this be simplified? Yes. I think your professor would accept this, so I'll circle this for now. But I also want to say this looks a lot nicer when you write it like this. In the numerator, I have 3/2, and then that x to the negative 1/2 power is going to be the square root of x in the denominator, right? Because a 1/2 power means square root. A negative sign means put it in the denominator. And then also e to the square root of x power, that's going to be in the numerator as well. Everyone see that? And this would also be another way of writing this final answer. Again, I think both are fine. It would only matter in a multiple choice setting. Okay. And with that, we're going to start looking at some of the more complicated exponential function derivatives. So I'm going to look at one that was similar to the one you guys posted in the chat. Let me know if it's not. I think it's similar. Let's say I have the function quantity x cubed plus 1 times e to the x squared minus 1 power. Is this pretty similar to the one you were talking about? Okay, I'll take that as a yes.
I think it was like e to the x squared raised to another exponent. Hold on, let me look.
Sure. You can get pretty complicated with some of these powers. Like right now it's just a product rule, which isn't terrible. Except most...
Yeah, so
Go ahead.
the example was e to the negative x to the positive 5th. Like raised to the raised. If that makes sense.
Can you say it one more time? Y
Yeah, so it
equals-
would be y equals, we'll just put x to the 5th.
Yep.
Plus 1 in parentheses. Like the whole thing in parentheses.
I don't think I'm following.
No, it's just like x to the 5th and
Yep.
then plus like 1 as a coefficient.
Okay, got
Yeah,
it.
sorry.
All good. And then this
And
is
then all
raised...
of that in parentheses. And then e to the negative x. And then raise that to the fifth.
Okay. Yeah, we'll deal with this example since it's hard and very fun. Okay, so the first thing I want to say is I would rewrite this just slightly. You would keep the x to the fifth plus 1. You're not going to touch that. We are going to use a product rule here. E to the negative x to the fifth. Remember what we said earlier. When you have a power raised to another power, what do? You multiply. You multiply. So it's e to the negative 5x power now. And now it's a lot more possible. Again, this is just y equals. This is not the derivative yet. Now let's take the derivative, y prime. Notice this is going to be a product rule where this is f of x and this is g of x. So if you remember what product rule says, I'm really hoping you know what product rule says by now, but it's going to be f of x, which is x to the fifth plus 1, times g prime of x. What is the derivative of e to the negative 5x power? Well, remember what we said earlier? I ask myself, what's the derivative of my exponent, negative 5x? It's negative 5. So negative 5 times my original e to the negative 5x. That's the first half of the product rule. The second half is g of x, which is e to the negative 5x, times the derivative of f of x. The derivative of x to the fifth plus 1, that's actually just an easy power rule. It's going to be 5x to the fourth plus 0, since plus 1 goes to 0. This is it. You can simplify it a bunch, I'm sure. I'm just going to keep this as the final answer. You get the gist. Any questions on that one?
No, thank you.
Great.
I just had a question.
Yep.
When you see E,
Yep.
like, I don't know when to differentiate from using, like, the ln. You know what I mean?
E versus ln. Are you saying that...
Like,
Go ahead.
I don't know how to, like, I see E and I kind of want to use, like, multiply it by ln to get rid of the E, almost. I don't know. If
Okay,
that
I
makes
see what
sense.
you're saying. So here's the difference between what you're saying and what we're doing right here. It really comes down to what is the question asking. What was the question asking at the first couple questions we were looking at where we did that strategy? The question was solve for x, right? If I want to solve for x, then I need to get rid of e. But in the derivative, e is our friend, not food, as Finding Nemo would say. Bruce, I think the shark's name was. But more importantly, whenever we have the derivative question, we don't take the natural log. That's just blatantly wrong. Well, actually, it's kind of a fun fact. You are going to, it's actually coming up in this class, I'm pretty sure. You are actually going to do that if you haven't done it already. It's called logarithmic differentiation. It's where the first step is you take the natural log of both sides. Those are monstrous problems, and we'll talk about that together, I'm sure, at some point. But today is not that day. All you need to do is say, hey, I'm asked to find the derivative. I am not going to write natural log, because the only time I do that is to solve for x. Does that make sense?
Yeah, thank you so much.
Yep, no problem. Okay, any other questions?
If you had to simplify this, how would you do it? Because that's what I was confused on.
That's a good question. So most people love to just say, oh, I'm done with this. I don't want to even simplify it. Those kids are lazy, and I'm glad you asked that question. So let's see what this would be if I simplify. There's two things I would say when it comes to simplifying that you need to be aware of. Number one, negative exponents need to go in the denominator for proper simplification. And two, you need to combine any coefficients you have and put them out in front of everything else. So what does that mean? Number one, this first term here, I see this negative 5 here. That's a coefficient. I'm going to write that out in front. Negative 5 times the quantity x to the fifth plus 1. That's in the numerator. And the denominator, I now have e to the positive 5x power, right? Because that negative sign becomes positive in the denominator like this. Then plus, there's going to be another fraction bar because I see the negative exponent. In my numerator, I just have 5x to the fourth. My denominator is e to the 5x power. You see that we have the same denominator here. If we wanted to, we could write this under just one fraction bar. So my numerator could be negative 5. I'll even distribute this negative 5 to both terms because I can do that too. Negative 5x to the fifth minus 5 plus 5x to the fourth. All of that is divided by e to the 5x. And at this point, you can factor out a 5. You can do a couple other things, but really this is about as simplified as we can get. Do you need to make it this simplified on the test? Probably not. I'd be surprised if you needed to. But in case you're curious, this is what I do. Again, the two strategies are, if I have a negative exponent, I'm writing that thing in the denominator. And if I have a coefficient, like my 5x there, then I'm going to write that out in front of everything else. Any questions?
Thank you.
You're welcome. Okay, now we're going to move on to some other fun problems. Anyone still writing? Good. Okay, so now let's keep going with derivatives. This time it's going to be, well, I don't want to tell you what rule it is, but it'll be a rule. Let's say I have f of x is equal to quantity e to the negative 2x plus 1. That's all going to be raised to the, let's say, third power. So for this one, you think about, what rule is this? What rule is this? Any takers? Any guesses?
Chain rule?
It is chain rule. How do we do the chain rule? Great question. So the derivative is going to be f prime of x equals, remember with the chain rule, I work from the outside in. What's the outer function going on here? It's this cubed on the outside. I deal with that first. It's a power rule, so I pull the 3 out in front, times the original function, e to the negative 2x plus 1. Now it's raised to the 3 minus 1 power, so 2. And after I do this, we're not done yet, then I'm going to multiply this. This is where the chain rule comes in. What's the derivative of my inside? E to the negative 2x plus 1. Don't shout it out. I'm sure some of you are smart. You don't need to prove it to the rest of us. The only person who has to prove that they're smart is me, and that's because I'm most important. Don't forget it. So again, I ask myself, what is the derivative of my exponent? Negative 2x. I know that derivative is negative 2. And then I multiply this by my original e to the negative 2x power. And then the derivative of the plus 1 just goes away. So that's it. This is a perfectly good final answer. Again, if you're curious on how we would simplify this, first I want to say this. Because of this squared out here, this whole thing, I'm going to circle in blue, this whole thing cannot be simplified like this part alone. Everything else can be, though. So I can combine this 3, I can combine this negative 2 to give me negative 6. I can also write this e to the 2x out in front, or e to the negative 2x. And then times the quantity e to the negative 2x plus 1. That whole thing is squared. And like I said earlier, if you want this to be as simplified as possible, you should put the negative exponents in the denominator. So I'm not going to... I'm deciding whether or not I want to. I don't care. I'm just going to keep it like this. You get the picture. Any questions? So again, this was the chain rule. And of course, we are going to look at a quotient rule problem. That's coming up right now. So here's the last derivative question I have for exponential functions. Let's say I have g of x is equal to e to the 3x minus 1 divided by e to the x. And I want to take the derivative of this. Now, if I wanted to, I would use the quotient rule. What does the quotient rule say? What does the quotient rule say? If my numerator is f of x and my denominator is g of x, then my derivative is going to be g of x times f prime of x minus f of x times g prime of x. Hopefully you all know this. Divided by g of x, that whole thing squared. Now, I've got some good news for us. We can, if we want to, we can do all of this. We can take the derivative of the numerator, denominator, plug everything into the formula, or we can use our properties of exponents and completely avoid the quotient rule altogether. What do I mean by that? Notice I have e to the 3x minus 1 divided by e to the x. Those numbers have the same base, which means I can rewrite this original function before I take the derivative as e to the 3x minus 1 minus my denominator, so minus x. This simplifies to e to the 2x minus 1. Now if I take the derivative of this, notice this is so much easier. So much easier. So always look out for that. Whenever it's the same base, see if you can simplify. It's going to make your life a lot easier. So now g prime of x, we can take the derivative. What's my derivative of my exponent, 2x minus 1? It's just 2. So 2 times my original, e to the 2x minus 1. There we go. Any questions on that? That's going to pretty much wrap up my talk on exponential derivatives. I'm going to move on to the next topic, which is logarithmic functions. So if anyone has any more questions, speak now or forever hold your peace. Okay. Love to hear it. Next up, we have logarithmic functions, the cousin of the exponential function. Logarithmic functions. We're going to be talking about how you simplify it, the properties of logarithmic stuff. Hopefully all of this sounds familiar from the quiz last Friday. And here's what it's going to be. Let's say I have f of x is equal to the natural log of x squared times x plus 1 divided by 3x minus 4. Something like this. How would I break this up into different functions? How would I do that? Well, remember, whenever I have multiplication in a natural log, like in the numerator here, for instance, I'm going to break this up into two different integrals like so. Natural log of x squared plus the natural log of x plus 1. So remember, multiplication becomes addition for logarithms, and then we can ask ourselves, well, what will the denominator be? How do we factor that in? If you didn't know this already, hopefully you did. In the denominator, it becomes minus, so minus quantity natural log of 3x minus 4. This is mostly it. There's one more thing we can do. I see here I have x squared, natural log of x squared. Remember, whenever I have an exponent here, like x squared, then I can take this exponent, write it out in front. This is not a power rule. I'm not subtracting 1. I'm just pulling this exponent out in front, so now it's 2 natural log of whatever was left inside, which is just x in this case, plus everything else is the same. Natural log of x plus 1 minus the natural log of 3x minus 4. This is as much as it can be broken down. You may be wondering, why do we want to know this skill? Why is it helpful? I'll tell you, it is very helpful whenever you want to take the derivative of logarithmic functions, and it's going to be the basis of why we do logarithmic differentiation, which, again, we'll talk about that later. Any questions on this one? Okay, great. Next up, let's say we have y equals, this time I'm going to go in reverse order. Let's say this time I have 3 natural log of x minus natural log of x squared plus 1 plus, let's say we have 5. And I want to bring this all into one natural log. How would I do that? So here's the first thing I'm going to do. I'm going to say to myself, this 3 can be written right here as x cubed. So really this is the natural log of x cubed. Now how do I factor in the minus natural log of x squared plus 1? Remember, minus means division, so I can rewrite this now as the natural log in the numerator, x cubed, denominator, x squared plus 1. We still have this plus 5 out here. How do we deal with that? Think about it for a second. Well, if we want to get this into our natural log, the thing we're going to have to do is we need to make this, well, we need to have natural log here. So here's what I'm going to tell you to do. Maybe you know this, maybe you don't. And hopefully this won't even come up on the test. This is actually kind of difficult. But what I'm going to say is I'm going to rewrite it as this. The natural log of e to the 5th power. Notice this is equal to 5. If you don't believe me, you can plug it in your calculator. The natural log and the e cancel out. All you're left with is 5. Why would I write it like this? Why would I bother? Because now I have natural log here. And it's addition, which means that's turning into multiplication. So in my numerator, I now have natural log of x cubed times e to the 5th. I do need to keep that e in there. Divided by x squared plus 1. This is going to be my final answer for that one. That one was kind of tricky, especially with the plus 5. But did that make sense? Any questions? Okay, great. Anyone still writing? So that's pretty much it for logarithmic functions. I don't think there's too much more to talk about. There is one more thing I want to mention, though, and that is how do we solve logarithmic functions? Kind of like how did we solve exponential functions? In other words, if I have the natural log of x equals 10, let's say, how do I solve for x? How do I solve for x? Well, to get x by itself, I need to take base e of both sides. I repeat, take base e of both sides. The e and the natural log cancel out. You get x equals e to the 10th power. And that would be how to solve it for this example. Okay? Any questions on that? Cool. So that's pretty much it for logarithmic functions. The next thing I want to talk about today is exponential growth and decay, which is definitely, in my opinion, besides optimization and probably curve sketching too, exponential growth and decay is one of the hardest topics that will be on this exam, in my opinion. Exponential growth and decay. I believe this is what you're learning right now in class. Does that sound right? What are you guys learning in class right now?
I think that's like the last thing we learned.
Okay. And will this be on the quiz test exam?
Yeah.
Awesome. So how do we deal with exponential growth and decay? How do we even know we're dealing with it? Number one, it's going to be a word problem. Number two, it's going to be talking about the population of a town. It's going to be talking about the population of a culture of bacteria multiplying. It's going to be talking about radioactive decay, half-life of elements, stuff like that. Things that just follow exponential growth and decay. They're growing exponentially. They're decaying exponentially. They're getting smaller exponentially. So here's an example problem with that. Let's say I have this question. The half-life of an element is 12 years. If I start with 100 grams of this element, how long does it take to reduce to 10 grams? I'll give you a couple seconds to write that down. The half-life of an element is 12 years. If I start with 100 grams of this element, how long does it take to reduce to 10 grams? So let's go ahead and get started. First, we're going to start with the main equation for this problem, which is, there's a couple ways you can write it. I'm going to write it like this, and you tell me if this is how you see it. Q equals Q naught, or Q sub 0, times e to the kt. Is this how you guys learned it?
Yes.
I think it was Q of X, but yeah.
Okay, perfect. So it really doesn't matter. Q of X, Q. Really, let's talk about what all these variables mean, because each of them are equally important and equally confusing. Actually, that's not true. Some are more confusing than others. So Q is, I want you to think of it as the final amount after some point in time passes. Q is the final amount. Q naught, the initial, is the initial amount. E is the number E. We all know it. K I'm going to skip. T is easier. It's time. And now I'm going to talk about K. So K, I'll tell you what K isn't. If they give you a percentage in the problem, like the sample reduces by 10%, the population grows by 25%, K is not a percentage. I repeat, K is not a percentage. It is known as the how do you spell proportion? Proportion? No, it's proportion. Sorry. Proportionality constant. It's just a constant. It's a number. The number itself means nothing. The number could be 0.1, 0.25637. The number means nothing. It just is the number that has to be in order for the math to work out. In other words, if you are figuring out K by reading the question, you did something wrong. The only way we can find K is by solving for it. The only way we can find K is by solving for it. Make a note of that, whatever you have to write. K is not a percentage. The only way we can find K is by solving for it. Now, luckily, we've got a lot more information here that we can use to solve for K in this problem. And that's what we're going to do. So let's go back to the question. Half-life of an element is 12 years. What does that mean? In case you don't know, half-life is a chemistry term that describes how long it takes for half of the elements or half of the atoms in an element to decay. So in this case, the element after 12 years, half of the atoms will decay. So using this equation right here, and we can even say the initial amount was 100, it doesn't matter. This is going to be true for actually any initial amount. But in the case that the initial amount is 100 grams, don't put final as 10, because let's just talk about actually, if you put the final as 10, because that's what the question's asking for. If you put final as 10, you put the initial as 100, e to the k times t, we're solving for t, and we don't know what k is. We have two unknown variables. This equation is not going to work right now. Don't use it yet. So instead, that's why we have the half-life formula. Because if the half-life is 12, then that means t is 12 here. That's where the 12 goes. And on the left side, the final amount, what's half of 100? 50. And now you can see here why this is going to work for any initial amount. In this case, it was 100 grams. It could be 1,000 grams. It could be 10 grams. It could be anything. Because whenever we divide by 100 here, we're always going to get 1/2 on the left side, which is why it's called half-life. Very cool. And that's equal to e to the 12k power. So again, I just divided both sides by 100 to get this. Now I need to solve for k. So to solve for k, again, this comes back to how we solve exponential functions. I need to take the natural log of both sides. That's going to cancel out my e here with the natural log. The left side does not cancel out, so I'm just going to leave it like this. Natural log of 1/2 equals 12k, which means k is equal to natural log of 1/2 divided by 12. Just because I'm curious what the decimal is, I'm going to plug this in my calculator. I don't know if you would have to actually plug it. If you're allowed a graphing calculator, or even scientific, I think scientific graphing calculator, just scientific. I think scientific calculators have the natural log button, so I think you can find it. It's negative 0.05776 is k. And obviously it goes to like 8 decimal places. I'm just going to write that many because it's fine. So now we found k. How does that help us? Remember what our initial thing we were trying to find was. We want to know how long it takes for the sample to reduce down to 10 grams. Now I'm going to say final 10 equals initial 100 times e to the k, which is negative 0.05776 times t. We're solving for t, and let's go ahead and do it. So first thing I'm going to do, divide both sides by 100. 10 divided by 100 is equal to e to the negative 0.05776 t. 10 divided by 100 is just 0.1, so I'll just write that there. Now again, I need to take the natural log of both sides, right? That's how I solve for t on the right. The left side does not simplify, unfortunately. So natural log of 0.1 is equal to negative 0.05776 t, or whatever your value for k was. And then t is going to equal the natural log of 0.1 divided by negative 0.05776. And again, I'm curious what this is, so I'm going to plug this in a calculator. Natural log of 0.1 divided by our value for k. We're going to get a time of 39.9, and the units here is years. And that's how long it would take for this problem. Any questions?
I just had one question. When you initially got 50,
Yes.
did you just, with the half-life?
Yes. I should have probably explained that more. But yes, the half-life, it's because if we started with 100, it means the half-life would be 50 grams.
Okay, and that's because we start with 100 grams?
Yes.
Okay.
And like
Thank
I said
you.
earlier, it doesn't matter what the initial amount is. I don't have to actually tell you what the initial amount is to find k. Because whatever the initial amount is, let's call it c, then the other side's always going to be 1/2 c. The c's cancel. Whatever c happens to be, it's always going to be 1/2 on the left side. Make sense?
Yes.
Great. And actually, there is one more thing I want to talk about with this equation. Where is it? So sometimes, this equation is very important. I'm going to box it and star it. I recommend knowing it inside and out. Tell me if I'm wrong, but have you guys seen it where it's e to the negative kt power? Have you guys seen that too?
Yes.
So let's talk about what's the difference between these two. First of all, it's obviously the same equation. One is for decay, the other is for growth. Negative is for decay, positive is for growth. Notice here, I used a positive KT. Is that blasphemy? Would I be crucified by your calculus teachers for doing that? Hopefully not. But pretty much what I'm trying to say is it all works out in the end because notice when I got K was a negative number. So we're all good. If I used e to the negative kt, then K would just be a positive number, right? So really it doesn't matter. The only instance where it would matter is where the question actually asks you to solve for what is the decay constant, what is the growth constant. In that case, you should probably make K positive. So I'm going to tell you this. If you notice that it's a decay problem, then yeah, technically I guess it should be negative KT. If it's a growth problem, leave the negative out. But again, it really doesn't matter. There are so many bigger things to worry about for this exam than whether you use positive or negative K. I'm going to tell you not to worry about it. Does that make sense? Okay. Anyone still writing or have any more questions on this one? Okay, we're going to no, go ahead.
Oh, sorry. How'd you get the ln in front of the 0.1 and then the in front of the e to the negative number?
This one right here? Like this step right here, right?
Yes.
So
Yeah.
let me erase it real quick and show you what I did. So I said to myself, I need to solve for t. And the only way I can solve for t is by getting rid of this base e. And the only way to do that is by taking the natural log of both sides. So I took the natural log of both sides. That is a legal math operation. I can do it. And when I do that, natural log and e cancels out. And that's how I solve for t. Does that make sense?
Yes, thank you.
Yep, no problem. Okay, we're going to look at one more example. This one's going to be worse. Not by a lot, but it's definitely harder. So let's say this is the next example. The price of a shirt grows exponentially. Spelled exponentially wrong. Exponentially with time. Let's say after 7 days, the price of the shirt increases by 15%. How long until the price of the shirt doubles? I'll give you a second to write that down. This also makes no sense in real life because shirts never go up in price like this. They always go down in price. They go on clearance. But let's say it's a really valuable shirt, and after 7 days, the price increases by 15%. I want to know how long until the price of the shirt doubles. Again, we're going to start out with the same initial equation. Q equals Q naught times e to the kt power. Since this is growth, exponential growth, I'm going to use positive k for this one. And now my next question is, what is k? What is k? You don't have to answer that out loud. You can just think about it. Do I know k based on the question alone? Can I find k? Really, what I'm trying to get at, is it this 15% number? For those of you who have been listening, you would know that I said k is not a percentage. It's never a percentage. They will never give you k in the problem unless they specifically say k equals 0.15. K is not 0.15. K is not 0.15. So don't make that confusion. What that's telling you, the price of the shirt increases by 15%. That's the final. That's this Q on the left side. The final price is 15% more than what it initially was. So notice I don't tell you what the initial price is. I don't need to tell you what the initial price is. All I need to know is that my final is 1.15 times my initial. Notice how I write this. 1.15. 15% more than 100% is 1.15. My initial price is Q naught. I don't care what the initial price actually is. It's going to work for any initial price. $1, $10, $100. It doesn't matter. On the right side, I still have my initial amount, which I never said, so Q naught, times e to the k, and t, I said this happens after 7 days. So again, the reason why I'm even writing this is because I need to solve for k. I need to, or else I'll never be able to figure out how long it takes for the price of the shirt to double. So the goal is to solve for k first. So notice Q naught cancels on both sides if I divide both sides by Q naught. Now I have 1.15 equals e to the 7k power. Now is the step when I take the natural log of both sides. On the left, that doesn't simplify. Natural log of 1.15. The right side does. We now just have 7k. And if I want to solve for k, I'm going to get k equals natural log of 1.15 divided by 7. Again, I'm going to plug this in a calculator because I can. See what it is. Natural log of 1.15 divided by 7. I get 0.0199, which is really 0.02. It's very close to 0.02. I'm just going to write that. 0.02. Notice, this is not 15%. K was not 15% because the percentage is never K. Got it? I don't know how many times I have to say that, but all of you, not all of you, some of you will still make that mistake, and I will get mad at you, and I will throw a temper tantrum, and please don't make me do that. Okay. So we found K. That's the first half of this question, already done. The second half is we need to figure out how long it takes for the price of the shirt to double. Again, we're going to use this equation again, but we're just going to change the variables around. This time, my final amount is twice my initial amount, 2 times Q naught. 2 times Q naught. That's what it means to double in price. On the right side, I still have Q naught times e to the kt power. And again, I know what k is. I can plug it in. It was 0.02. 0.02. Notice here, it does not matter what the initial price of the shirt was. Again, because Q naught cancels, I get 2 equals e to the 0.02 t power. And now to solve for t here, I'm going to take the natural log of both sides. Some of you say ln. I will always make fun of you people because ln had her own TV show and that was canceled. This is called the natural log. Is it a dumb joke? Yes. Did my high school calculus teacher make that joke all the time? Yes. So I will naturally do it as well. Let her legacy live on. She still teaches. Whatever. T is equal to natural log of 2 divided by 0.02. I'm just going to plug this in a calculator. And we'll get a final answer of natural log of 2 divided by 0.02. Before I hit enter, I'm going to take a guess because I love mental math. So natural log of 2 is approximately, I think it's around 0.9. And when you divide by 0.2, it's the same thing as multiplying by 50. I'm going to guess my answer is 50 times 0.9, which is 45. Let's see if it's close to 45. Not even close. Horrible. So the answer is 34.7. And that's going to be days. It takes 34.7 days for this to double. I know where I went wrong in my mental math. Natural log of 2 is definitely not 0.9. I thought it was closer to... Yeah, it's not. Okay. Whatever. I look like an idiot. That's okay.
I have a question.
Yes.
Why did you decide to use Q naught in place of Q on the left-hand side of each equation?
That's a good question. So I'm saying my initial price is Q naught. I'm saying my initial price is Q naught, my initial whatever it is. I don't know my final, right? So I'm writing my final in terms of my initial. If you want to...
Okay, that makes sense.
Okay. And also, if you want to, since I don't tell you the price of the shirt, if you want to, you can even make up a price. $50, $100, whatever. It's going to work. Because again, if they don't tell you the price or they don't tell you the initial amount of grams in the HalfLife sample, you can just plug in a number. It's going to work. It's very cool.
Also, why did you put a 2 in front of the Q naught in the second part?
Right here, right?
Yeah.
That's because I'm saying the final is double. I'm saying the price doubled.
Okay.
Any other questions? Yep.
I had one, like in the very beginning when you got you multiplied 1.15.
Yes.
How did you get that?
Yeah, that's because, so this is honestly, in my opinion, the hardest part of this problem is coming up with this initial equation. It's because the price went up by 15%. And remember, the left side's the final. So I'm saying the final price is 15% more than Q9. How do you write 15% more? Technically, it's 1 plus 0.15, so I wrote 1.15. Does that make sense?
I'm just confused on how you got the 1.
Okay, fair enough. So let's say this. Let's say I didn't have the 1, because that's actually a good question. If it was just 0.15, Q naught equals, what, Q naught times the rest of it, I'm saying that the final price is literally 15% of my initial. In other words, the price went down. The price went down to 15%. I'm saying the price increased by 15%. So I need the 1 plus, because if I don't, I'm saying the price went down.
Okay. So then if it was asking if the price decreased, you would disregard the 1 and just do the point.
So that's actually a good question. It depends on how I ask it. If I'm saying the
Okay.
price went down by 15%, if I'm saying the price went down, I'm saying 1 minus 0.15, like this.
Okay.
However, if I'm saying the price was 15% of the original, that's when I would say 0.15. So notice the wording. This is saying decreased by 15%. That's what this example is. And this example, where it's literally 0.15, I would say 15% of the original. The wording in this question can get very annoying. The only way you're going to get better is by looking at more example problems and, doing more problems. But does everyone see the difference here? It's a very good question. I should have touched upon that.
Thank you.
Yep. Any other questions? So that's pretty much it for exponential growth and decay. We're doing great on time. This is about exactly where I wanted to be at this point. So that's gonna wrap it up for exponential growth and decay. For the last half hour, I want to talk about pretty much everything else: extrema, curve sketching, and optimization. I do want to start with curve sketching, because I think curve sketching is like the hardest thing in this class, because it's not easy. It's not something you can just plug into the derivative. What is curve sketching? It's this. Let's say I have the function y equals x squared minus 2x plus 4, and I wanted you to plot this. I want you to plot this. I mean, this is a quadratic function. We know it's a parabola opening upwards because the leading coefficient is a positive 1. That's not too bad. But what it really comes down to with curve sketching is figuring out, using the derivative, what this function is going to look like. So I do want to talk about that right now. Let's say I have this function y equals x squared minus 2x plus 4. We'll do this example. I'm going to call this section curve sketching. Curve sketching. So if I want to see what this graph looks like, the first thing I should do is take the derivative, y prime. We'll talk about y in a second. Y prime equals 2x minus 2. That's my derivative. Now I want to find the critical points. And what does it mean to find the critical points? It means set it equal to 0, solve for x. 2x equals positive 2. X is going to equal 1. What does a critical point mean again? Someone can actually answer this. I want someone to tell me, what is a critical point? There's a bunch of correct answers, but someone please answer it. Don't make me call on names. I know some of your names.
Is it where like the behavior of the function is changing?
That's a good answer. That's not a bad answer, at least. I'm just going to say it. It's where, first of all, the slope is 0. It means a bunch of things. So critical points, I'm going to say what a critical point is. There's like 3 important things for a critical point. I know you know it. You may just not know all 3 things. So the first thing is the fact that the slope is 0 at this point. Slope is 0 or vertical. It can also be vertical. That's the first thing we know about critical points. The second thing we know is this is where the maximums and the minimums occur. So if you want to find a max or min, it has to happen at a critical point. It has to. And the third thing special about critical points, it's where the function switches from increasing to decreasing and vice versa. So the three things are the slope is 0 or it's vertical. How can you tell if it's 0 or vertical? That's actually a good question. So I'll talk about that right now. If we have f prime of x equals, let's say x, you set that equal to 0, this is going to be a slope of 0 right here at x equals 0 because it's in the numerator. If, let's say I have f prime of x equals x plus 1 over x minus 2, the numerator I said equal to 0, that is where my slope is flat. Slope is flat. Slope is vertical when the denominator equals 0. Slope is vertical. So the slope is vertical when the 0 is in the denominator. The slope is flat when the 0 is in the numerator. Make sense? Okay. So going back here, critical points. The slope is 0 or vertical. That's where the maximum or the minimum occurs. That has to do with the first derivative test and plotting the number line and seeing where the sign changes, all that stuff. And then the third thing is it's the function switches from increasing to decreasing or decreasing to increasing, same thing. Pretty much the critical point is where all the interesting stuff in our plot is going to happen. And now let's go ahead and do it for this example. We have x equals 1 here. That's our critical point. That's our critical point. So what's going on at x equals 1? To find out, I am going to make a number line. So I make a number line here. I call my number line f prime of x because that's the function I'm plugging into, the derivative. And I got x equals 1 here. Now remember my derivative was, I think it was 2x minus 2. Yeah, that's right. So now I need to plug in points around 1. Let's start with a number less than 1. How about 0? 0 is a great choice. So f prime of 0, plug in 0, it's just going to be negative 2. Now, I do not care about the fact that it's negative 2. All I care about is the fact that it's negative. Negative. What does that mean? When I have a negative first derivative to the left of 1, it means that this function's decreasing. It means decreasing. Decreasing. Then greater than 1. Let's plug in a point like positive 2. F prime of 2, we get 2 times 2 minus 2. I get positive 2. Again, I don't care about the positive 2. I just care about the fact that it's positive. So positive in this region, it means it's increasing. So now I've got a pretty good idea of what this function looks like. By the way, this is going to be a minimum at x equals 1 because decreasing followed by increasing looks like this. And that is going to be a minimum. So now I've got a pretty good idea of what this function looks like. I can tell you that at the point x equals 1, it's going to have a minimum. I also know that the y-intercept, this is kind of getting into the nitty-gritty of it, but if my initial function was this, and I see the plus 4, then it means my y-intercept was plus 4. In other words, I cross the y-axis right here at positive 4. I'm not sure if you need to know that. If you want to, you can even just plug in a few points to get a feel for what this graph looks like. Like for instance, if I plug in x equals 1 here into my function, x squared minus 2x plus 4, it would be 1 squared minus 2 plus 4. I'd get positive 3. So the point right here is 1 comma 3. 1 comma 3. I know it's increasing to the left, and I know it's increasing to the right. I'm sorry. From the left, it's decreasing. Like we all see, it's decreasing until it gets to positive 1. Then it starts increasing. And we know that because of, again, our number line. So this is kind of an easy example in my opinion because we all know what an upward shaping parabola looks like. I just wanted to start with an easy example. Now let's look at a harder example, one that's really going to make your skin crawl. Was everyone done writing? Sorry, I should have asked that.
I'm sorry, could you go over how you got the 4 and the 1 comma 3 again?
Yeah, sure. So that's where I just went back to the original function. And I said y equals x squared minus 2x plus 4. To find the y-intercept, you set x equal to 0. So if you set x equal to 0, you get 4. I just wanted to see what the y point was at 3, just so I could draw a decent graph of this. Or I'm sorry, I meant x equals 1. And when I plug in 1 here, I get y equals 3. Does that make sense?
Yeah, that makes sense. Thank
Okay.
you.
Yep. And I mean, you can do that for sure. In general, though, they don't want you to be specific with these curve sketches. They just want a general outline of what this thing will look like. And a lot of times it's actually multiple choice. You want to pick from the following options. And so especially when that happens, I mean, you don't have to plug in points. You can, if sometimes, yeah. I mean, sometimes it is easier to plug in points, but in general, they want you to look at the derivative. They want you to, the whole point of calculus is, can you use slopes to identify, well, various things. So it's a very useful skill to have. So that's it for this one. Let's go ahead and move on to the next one. I want to make it harder, up the ante a little bit. Let's say I have the function y equals x plus 1 over just x. And I want to know what this function looks like. So for this one, since we have a fraction bar, I do want to talk about horizontal and vertical asymptotes as well. I'm going to say HA for horizontal asymptote, VA for vertical asymptote. If you don't know the abbreviations, please write them out. I don't want you to look at this later and see ha and va, and you don't know what those mean. Write them out if you don't think you'll remember. But a horizontal asymptote, we all know what it looks like. It's where, you know, the dashed horizontal line on a graph. Vertical asymptotes are the dashed vertical line. How do we find them? The vertical asymptotes are easier. For that, you set denominator equal to 0. You're going to set the denominator equal to 0. That's how we find vertical asymptotes. So for this one, if I set the denominator equal to 0, it's just x equals 0, and that's literally it. There's my vertical asymptote. Very easy. Now if I have a horizontal asymptote, here's how we're going to find it. Horizontal asymptote is literally the same question as what is the limit as x approaches infinity. We go back to our limit days, our limit at infinity days. I ask myself, what is the limit as x approaches infinity of x plus 1 divided by x? Hopefully you remember your rules of limits at infinity. I know it's been a while, but I think you need to know them, especially for horizontal asymptotes. So since the degrees are the same, it's x to the first power in the numerator, x to the first power in the denominator, what we're going to do is look at the coefficients. So in other words, since it's both x and x, like if there was an x squared in the numerator or denominator, that's going to mess us up. But since it's the same degree, they're both x. It's like we have a 1 in front of the x here, it's a 1 in front of the x here. That means my limit is going to equal 1 divided by 1. So just 1. I have a horizontal asymptote at y equals 1. That's another thing worth mentioning. You have x equals for vertical asymptotes and y equals for horizontal asymptotes. So definitely review in your notes if you don't remember the other two scenarios, when the denominator has a higher power, like x squared, or when the numerator has a higher power, like x squared. You need to know what to do in those cases as well. If you remember, numerator's higher, it means does not exist. In other words, no horizontal asymptotes. Denominator degree is higher, that means it's y equals 0 is our horizontal asymptote. So make a note of that if you don't remember. And that's it for the horizontal and vertical asymptotes. So if I were to draw a graph of this, I've already got a pretty good idea of what this will look like. Got a pretty good idea. I know that there's x, y-axis. There's a horizontal asymptote at y equals 1. So that point right there is 1. And then I know there's a vertical asymptote at x equals 0. So it's kind of hard to see, but I drew a dashed red line along my y-axis. And it means the graph is going to approach but never touch those red lines. Now, how do I know what the rest of this graph looks like, right? That's a good question. You already know the answer, or at least hopefully you do. It has to do with the derivative. We're going to take the derivative of this. So again, the original function was y equals x plus 1 divided by x. So I need to take the derivative of this. Y equals x plus 1 over x. Let's do a quotient rule. So it's going to be derivative of the denominator. So y prime equals, I'm sorry, I already said it wrong. It's denominator times derivative of the numerator. So x times derivative of x plus 1 is just 1. Minus the numerator, x plus 1, times the derivative of my denominator, which is just 1. divided by the denominator squared. So here I have, I'm going to simplify the numerator. I get x minus, I'm distributing this negative sign to both terms. So x minus 1 divided by x squared. Everyone see that? This actually is going to simplify to negative 1 divided by x squared. And now, again, whenever I have a fraction bar with my derivative and I want to find my critical points, I'm not going to set this equal to 0. If I set this whole thing equal to 0, I multiply x squared on both sides to cancel out the x squared, right? Multiply both sides by x squared. You get 0 times x squared. That whole thing 0, you lost some of your solutions. That's not good. So instead of setting the whole thing equal to 0, I'm going to set both the numerator and denominator equal to 0. We see here that setting the numerator equal to 0 is just complete nonsense. It doesn't make any sense. And x squared equals 0, I'm just going to get x equals 0 after I take the square root. So there is my critical point. Notice the critical point is the same thing as the vertical asymptote. That is going to happen a lot. Actually, all the time. So critical point is the vertical asymptote. A lot of the time. Remember, you don't find it the same way. To find critical points, you need to take the derivative. To find vertical asymptotes, you just set the denominator equal to 0. So next up, remember, number line. So number line here, I have x equals 0 on my number line. And again, my function y prime was equal to, we got it simplified down to negative 1 over x squared. That's pretty good. And now to see where the point's positive and negative, I'm going to plug in a negative number, like negative 1, let's say. So y prime equals negative 1 divided by negative 1 squared. That's going to give us a grand total of negative 1. And since that is negative, I'm going to put a negative sign here on my graph. Now let's deal with a number like positive 1. So y prime equals negative 1 divided by positive 1 squared. It's still going to be negative 1. It's going to be negative. Notice it's negative everywhere. It's negative everywhere. It's decreasing everywhere. I'll even make a note of that. Decreasing everywhere. And we also know that there's a vertical asymptote at x equals 0. So now, oh, notice, is this a max or a min at x equals 0? It is neither, because it's decreasing on both sides. It's neither. So I'm going to go back up to the graph I was drawing here. So it's decreasing everywhere. So from the left side, I'm decreasing, which means I'm on this side of the asymptote. And then after 0, I continue decreasing. And the only way that's possible is if I'm continuing up from infinity and going towards the horizontal asymptote right there. This is what this function is going to look like. I know this is true because this function is decreasing everywhere. This is why the derivative is so powerful. I can come up with a graph of pretty much any function as long as I know how to take the derivative of it. Any questions on this one? Okay, anyone still writing?
I have a quick question.
Yep.
Can a line cross a horizontal asymptote?
Yeah, it actually is possible for that to happen. But I'm trying to think of an example where that happens. I know I've seen it before. I'm going to tell you, you're not going to see it on the test. Unless it's a piecewise function. You know what I mean? A piecewise function can do it because, well, the left side can be literally different than the right side. I know I've seen examples where it approaches a horizontal asymptote. I just can't think of it right now. Does that answer your question?
Yes, thank you.
Yep. Okay, and now I do want to, we have 15 minutes left. I'm going to probably not go all the way to 9:30 because I've pretty much said everything I've wanted to, except for one more thing, and that's curve sketching of exponential functions. In other words, I want to identify what the exponential or the logarithmic function looks like. Because there's 4 possible functions we can have here. We have y equals e to the x, y equals negative e to the x, y equals e to the negative x, and y equals negative e to the negative x. 4 different scenarios, 4 different graphs. Let's quick sketch all of these real quick. Y equals e to the x, hopefully you know what that one looks like. This one, I'm going to draw it in blue, looks like this. If you know the base, the parent function, oh, and there's a horizontal asymptote in all of these functions because e to the x has a horizontal asymptote. Y equals e to the x is our parent function. We're going to base the rest of these on this. Here's the next one. Y equals negative e to the x power. So again, I have a horizontal asymptote here. I want you guys to think about this for a second. Take like 30 seconds. Think about this. I want you to draw it on your paper. I don't care if you're wrong. I will make fun of you. Yes, I will. But I can't see you, so it's kind of hard for me to make fun of you. But I'm assuming half of you will make the mistake, so don't worry. I've got you covered. So go ahead, give it a try. Sketch it. Okay, that felt like 30 seconds. Or at least, I think if you didn't get it by now, you're hopeless. Sorry. But negative e to the x is literally a flip along the x-axis. Like, if all of my positive points became negative, in other words, this is what negative e to the x looks like. If you didn't know that or you're struggling to memorize it, my advice to you is just try and memorize it. Don't try and think it through logically if it doesn't make sense to you. Just memorize it. Okay, now the next one. Oh, sorry, I forgot to make... So for those of you who got that wrong, you're dumb and you have no hope in calculus. There, I properly made fun of you. You're welcome. Now the next one. Y equals e to the negative x. Again, horizontal asymptote here. And now I need to draw this one. Go ahead, give this one a shot. I'll give you 15 seconds on this one. I am not using a timer. So the function time's up. So the function y equals e to the negative x is a flip along the y-axis, which means it's going to look like this. And by the way, even though it's y equals e to the negative x, remember that function is really just 1 divided by e to the x. Question, when is this ever negative? The answer is never. You can plug in any value for x. E to the x is always positive. It's always positive. You're not going to get a negative answer anywhere. So the function is always above the x-axis. It's always positive. And now for the last one. It's the only one we haven't drawn yet, so hopefully you can figure it out, even if you got the other two wrong. Let's see how bad you can mess this up. I'll give you 7.5 seconds. Okay, time's up. So this one's going to be both a flip along the x-axis and the y-axis. It's going to look like that. Okay, so again, I would recommend just memorizing these. It's honestly, it's not that bad. It's just 4 little things, but easy points on the test. Any questions? Okay, and now the last one I want to look at is same thing but with natural log. And this time I'm actually going to ask it slightly differently. This time I'm going to give you the graph and you're going to tell me what the function is. Ooh, this is fun. So this time I'm going to give you vertical asymptote and the function looks like this. Which function is this? Actually, I'm going to tell you this is the parent function. This is y equals natural log of x. Some of you probably knew this already and I'm sorry I had to take your thunder, but I'm smarter than you, so it doesn't matter. Yes, I have a inferiority complex, in case you're wondering. So y equals natural log of x. This is that function. Now here's the next one. It looks like this. And there's a vertical asymptote right here. So it's either, your answer choices, I'll give you the answer choices. It's natural log of negative x, negative natural log of x, or negative natural log of negative x. Which one is it? Okay, so for this one, notice it flipped along the y-axis, which means this is going to be y equals natural log of negative x. Hopefully, I mean, I can't give a better explanation than that because a lot of this is kind of just memorization, knowing where the negative goes and what that means on the graph. But does anyone have any questions on that one?
Can you just explain the like what ones flip on the horizontal and what ones flip
Got it. Okay,
one more
so
time?
this is going to be I'm going to say a horrible explanation. But actually, it's not that bad. But it's the opposite of what you'd expect. It's the opposite of what you'd expect. So I said this is a flip along the y-axis. Does everyone agree with that? Person who just asked that question, do you agree that this is a flip along the y-axis?
Yeah.
Okay, if I flip along the y-axis, it's the opposite of what you expect. It means wherever I see x, I replace it with a negative x. I replace the x, in other words. I don't replace the y. Now I'm going to scroll back up real quick to the e to the x example, like this one right here. This one I said was an x-axis flip. We see that here's the x-axis right here, and it flipped along the x-axis. So because I flipped the x, I'm flipping the y value. And whenever I say flip the y value, it means I'm putting a negative sign at the very end or the very beginning. Notice it's not touching the x. I did not put a negative sign in front of the x. Does that make sense?
Yeah. So you flip across the y-axis when you change the x value.
Yep.
And then flip across the y-axis when you change the x.
Yes. And again, it's confusing. I know it's confusing. I would honestly just recommend memorizing it. Here's the next one. Remember what we said about the y-axis and the x-axis flip. If I flip along the x, I'm changing... you remember, boys. If I flip along the x-axis, then it's going to be a change in the y value. If I flip along the y-axis, is a change in the x value. Having said that, let's see if you can get this one. It's this function right here. And again, the parent is right above it. So what's it going to be? Go ahead and give it a shot. This is going to be both. It's a flip along the x and the y-axis. So it's y equals negative natural log of negative x. And then I'm going to tell you the last one. We already know it. It's the only one left. It's negative natural log of positive x. Go ahead and see if you can draw this one as the last one. Notice we know it's a negative sign here out in front of the y value. So it should be an x-axis flip. Let's see if you can draw an x-axis flip correctly. And if not, it's the last shape we haven't drew yet. So, okay, time's up. It is going to look like that. Okay?